This video has for purpose to explain how to represent simulation models using algebraic equations. During this sizing course, we have seen or are going to see different model types: estimation, simulation, and evaluation ones. Different ways to implement them exist. This graph describes three possibilities. 1. Every model is in a computation environment, which is purely algebraic, such as spreadsheets. 2. Every model is in a computation environment which uses differential equations such as Modelica. The third one consists in a mix of both. The first solution is more advantageous regarding optimization time and also gives the possibility to consider many design drivers. The second solution enables us to use more complex and more exact simulation models, but often implies too important simulation times when it comes to optimization. A third solution is to use MetaModels, which are less time-consuming. These MetaModels are often algebraic equations. This method has the advantages of the two previous ones, but we must be very careful about the accuracy of the MetaModels we use. Surface responses are built using polynomial approximations that are obtained by regression on a dataset. This approximation function has for input the design parameters of the model and for output the model response. Design parameters xy are characterized by variation domains that can have different amplitudes. Modeling using design of experiments by substituting variables normalizes these domains between -1 and +1 for all the parameters. This normalization makes it easier to compare the effects of different design parameters and to demonstrate study and modeling methods. A surface response model includes a constant mean value, linear terms which give the main effects of the variables, a term of crossed products which gives the possibility to consider the interaction between the variables, and higher order terms to reduce errors if necessary. To estimate Bij parameters, we need to carry out experiments and simulations on the numerical model. The experiment choices must minimize the modeling error. The complex model evaluation is done using specific values on the model's input variables, here x1 and x2. Therefore, we get values of the output we are interested in. This generates a set of statistic data that can be used by statistical analysis tools such as linear regression or the methods of least squares. We face different types of design of experiments. A two levels full factorial design. All levels exist the same number of times. They require nk experiments, k being the number of parameters. A fractional factorial design. Orthogonal planes. All the possible level combinations are not done because the estimation of the model's coefficient do not require it. These two types of planes are ideal to model principal effects and interactions. A central composite design. New experiments are added in order to be more adapted regarding models which have quadratic terms, and a full factorial design with x levels and Latin hypercube designs, only for all models with orders higher than 2. A metamodel establishment goes through these steps. 1. The simulation model design, choosing design parameters and response parameters. Then, we have to reduce the number of design parameters if necessary, using dimensional analysis and or by determining the most important parameters. It's a two levels design of experiments. We can also choose to have more detailed design of experiments, more adapted for regression. Then, we have to choose the shape of the regression function and the transformations to be applied to the data. We actually execute the regression, then evaluate its quality, and finally, we're able to implement and use the MetaModel. During the preliminary design of an air brake actuator, it is useful to compute quantities used during sizing, such as stroke, acceleration, and efforts. This example concerns the mechanical model of the spoiler and links the mission profile angular position of the surface to the effort and speed the linear actuator has to deliver. The software used for this example are Dimola Modelica for system simulation and multi-body modeling, and Optimus for design of experiments and linear regression. Optimus is one of several software for multidisciplinary optimization, or MDO, and gives the following possibilities: interfacing and driving simulation software, sequencing different computation types, design of experiments, MetaModels, optimization, robustness analysis, and many more. The simulation model uses components of Modelica's multi-body library. The inverse simulation that Modelica offers gives us the possibility to obtain effort-speed profile that Jack has to fulfill using angular displacement mission profiles at spoiler level. We find that way the quantities that are used and computed in an analytical way. More complex models could also be simulated. The model is parametered using the 6 design parameters. We can calculate means and detect the extreme quantities that are useful to compute the important quantities for sizing. The Optimus model represents the chaining method that must be executed in order to establish meta-models. Design parameters definition, updating Modelica files with these parameters, launching a time simulation, and retrieving responses in a result file. The first design of experiment is a 2 levels full factorial design for the input variables. That means 2 to the power 6, or 64 experiments. It's going to help us study the influence of the different design parameters. This array represents a correlation analysis of the input and output data. We see that for each output quantity, only 4 or 6 parameters are important, and therefore have to be considered. For example, in the case of the stroke computation, lever X, lever Y, anchor X, and anchor Y. For the final regression, we use latent hypercube. It gives us the possibility to multiply the number of levels of the input variables while limiting the overall number of experiments. A first regression, computing the RMS effort from anchor points, has a mediocre regression quality. The observation is confirmed by the dispersion points around the curve y equals x, which compares the simulation results and the computed function. A transformation that expresses the inverse of this effort in function of the anchor points improves the regression quality. This type of transformation can also be done on the inputs of the model. Once the regression coefficients are computed, the polynomial functions can easily be implemented in any algebraic computation environment, such as Microsoft Excel.